Welcome back to the third video in the series ARM Exceptions, Gotta Catch Them All. It has been a couple of weeks for me since the last video, but today we continue with the list of exceptions that we want to try to catch. Small recap, we're trying to catch all exceptions that the ARM Cortex microcontroller has. In previous videos we checked most of the lower exceptions, and currently we're only left with the debug monitor, enemy, and the reset. It's not really an exception, but it has an exception, or it has an exception handler. So for completeness we try to include it as well. So only a couple things left. Debug monitor, not sure if I'll attempt this one, but we'll see. So I'll continue with the enemy and the reset today, and I think this will be a short video. Yeah, as said before, it has been a couple of weeks since I worked on this, so I probably have to refamiliarize myself with the code and what we're doing exactly, but yeah, we go there as we go. So let's see what we got until now. So let's run this, and this is where we left the previous video. So we create a program that shows all the entries of all the exceptions that occur, and currently we stack them up on one big call stack, and the last exception that we triggered was the hard fault, and that matches with the checkoff list that we have here. And then in the hard fault we set a breakpoint, and then the cargo run of the, what's it called, cargo probe, of the RS probe, that's used with cargo run, catch this breakpoint and shows a small stack trace. But this is also working as expected, and let's see the code. So I have to find the hard fault. Yeah, so here's the breakpoint. So this is where we left. Okay, so the next step is to trigger an enemy, so a non-maskable interrupt, and yeah, maybe first figure out what it really means or when it's triggered. So open the documentation and hope it has something to say about it. Oh, here it is. So a non-maskable interrupt can be signaled by a peripheral or triggered by software. Okay, it has the highest priority, other than reset. Okay, permanently enabled, yes. It cannot be masked or prevented. Okay, but what causes it? Fault handling, usage fault. So I think the non-maskable interrupt can be triggered when something is really wrong. Oh, here. When executing the lockup state. No. Okay, so not totally clear when the non-maskable interrupt is triggered, but looking at our code, it looks like we already hit it once because we have installed a handler for it. So I wonder what happened the last time. But I think so the bus fault goes into hard fault. Maybe it's just as easy as just triggering yet another fault. So when looking at the call stack, we see that we go from users fault, bus fault, memory management fault, and then into the hard fault. And how we get into the hard fault is by executing or trying to execute a function that is in some non-execute memory, but that is done within the memory management fault. So this is the exception that is responsible for catching faults caused by this. So if we again trigger it, the only higher level up is the hard fault itself. So maybe if we try to trigger this yet another time, we trigger the enemy. I don't know. We can try it. So let's see. If I add this here, what happens? Okay. Unrecoverable exception. What's up with this? Let me try pushing reset on the board. Don't know if that helps. Nope. Okay. So at least something is happening, but it's not very clear what is happening. Yeah, so maybe add this back and use GDB to see what's going on. I hope this is still in the history. Looks like it. This. Target remote. Okay. Oh, did I save this now? Save. Maybe and a breakpoint here as well. Something like this. Rebuild it. Cargo build. Okay. Now we can load field. Okay. Why is this? What's going on? Load. Oh. Remote. Connect to the target. Yes. Then try to load, and we cannot load it. Load field. Is this this running? Yes, should be. So what's the problem? Not sure, maybe just run it once. Loading, did loading. Here the loading does work. Okay, but now it should be updated with this code. Then we can use the GDB server from Propares and then reconnect to it. And we can reset the chip. Oh. Reset. Monitor command not supported. Okay, now I'm connected. Now I can reset. Or maybe reset fault. Yeah, and then continue. And then break it. Oh, it thinks it ends up at that place, but that should not be right. Let's see. Okay. Yeah. Not sure what's going on. If I, let's see, if I place the breakpoint before the call is in the hard fault handler. Okay, that works. Reset fault and then continue. It does not end up there. What? Trying to reset the board externally, but it's not doing a lot. What's going on? Reset, resetting target. Okay. Yeah, something's not happy with this. But previous times, yeah, it got captured by an exception, but this time it does not. So maybe no, yeah, we already knew we would get here. So quit. Yes. Oh, locked up. Core is in a locked up state due to the result of an unrecoverable exception. Ah, okay. So we get into the lockup. Okay. This. Okay. Lookup state if a fault occurs when executing the enemy or hard fault. Okay. So it seems that does not, when the is in a lockup, it does not execute any instructions. Processor remains in lockup states until either it's reset, an enemy occurs, or it's halted by the debugger. If a lockup state occurs from, okay. Sure. So can we verify this somehow? So I think we should be possible with GDB. So let's reconnect to the target. I want to see let's connect. Okay, I want to see if this is visible in the status of the registers. So we should be able to do a software reset from within GDB or GDB by running mon reset. And halt should immediately break it. And maybe if we place a breakpoint at main, we can try to continue. Okay, and now we hit main. So currently we should not be in a lockup, and I hope this is visible with the by dumping the registers. Info rechts. Reg. So this one. Okay. Yeah, this is not really descriptive, but my guess would be that some of these, or maybe the status register, has a lookup flag or something like that, or maybe it's only available in the debug core. Or wait a minute, there is a, where did I see this? The status, you can query if the core is halted or is running or stuff like that. And that's, I think that's in info. Oh. I'm used to running a GDB with OpenOCD, but now I'm using it with ProPRS, and it has a lot less commands available when using the monitoring subcommands. So I'm not sure if I can query the status of the chip. Oh, what is this? Okay, thanks, I guess. What the fuck? Okay. Yeah, very nice. No, I cannot break it. Program page. Huh. Is it dumping its memory or something? I don't know. Yeah, okay. Wait. But if we can trust this, oh, it was partially closed. Okay, whatever. It's in the looked up status, and that that matches up with the description that is that's here. That where was it? Lookup. Dus if a fault occurs when executing an enemy or a hard fault, and we were in the hard fault already, and we triggered another exception, so that causes a lockup. But here it says that the processor remains in lockup state until either it resets or an enemy occurs. So going or triggering an enemy from the hard fault should always should work, I guess, because an enemy is an exception in the hard fault handler, so it should lock up, but it also prevents the lockup when going to the enemy. So next question is, okay, what is this enemy, and how do how do we trigger it? It said that it was triggerable via software, so maybe it just has a flag. That's boring, but okay. So system handlers. Asynchronous. Okay, maybe just look around and see what we get in the manual. Okay. Oh. Before. Yeah, sure. Set pending bit for non-maskable interrupt. Okay. So that is a set pending. Oh yeah. Enemy pending set. Pend set. Oh wait, but that's. Yeah, set pending should make it pending. It's not read only to see if it is pending, I guess. So let's see. A set pending bit. Write has no effect, or write of 0 has no effect, but the write of 1 changes the enemy exception state to pending. Oh, and you can read it to query the flag itself, the bit. Sure. As soon as you write 1 to it, it will trigger because it has the highest priority and it's a fixed priority. So this should work. So let's try this. So we're going to set the enemy pending, the enemy pend set bit in the interrupt control status register. I think we already used this before, so it should be an easy copy paste from somewhere. Let's see. Or maybe not. Doesn't look like it, but oh well. So this one, oh, and maybe is setting a breakpoint in the, no, that should work because we already did it before. Strange. Yeah, I was thinking now, right? So setting a breakpoint would also trigger the exception. So that should also be a lockup. But in the previously we saw that that worked, so that's kind of confusing. Oh, it still works. So, oh, maybe because the debugger is handling the breakpoint exception, it's fine because the debugger could also get the system out of lockup. So this is no longer needed because this will cause the lockup, and we will try to set the most significant bit of this register. Yeah. Yeah, so we need something like this. Oh, maybe this is it. Yeah, this is what I was looking for. And instead of writing bit 28, we want to write bit 31. And this is set, what did we say here? Yeah, I set that big flag, but okay. Set enemy pend set bit to trigger enemy. Okay. And that should be it. So let's test it, and then that or this exit code can be removed because it will never be executed. So let's see. Alright, yes. So we now get into the enemy. Nice. I still wonder why. What's the use case for this then, if you have to set it manually? I would imagine that this would also trigger on its own when some condition is met, because don't really see the use case for triggering it manually. But okay, for now this is fine. So alright, this is already it, so we can check another thing off the list. Nice, mark that as done, and then we have one final exception to trigger. It's not really an exception in my opinion, but I wonder what the manual has to say about it. Let's see, exception, so the reset. Exception type reset. It's a special form of exception, sure. Okay. Yeah. I can imagine that it maybe. No, because, okay, so we want to stack all our exceptions and have one big chain of exceptions on the single stack, and the reset is our last exception that we want to trigger. But yeah, it's a special form of an exception, but it's also special in the other way, because I think the hardware is designed to not only update the program counter, but also the reset, no, also the stack register, with the, because that value is also in the interrupt vector table. But we can try to see what happens, and maybe it does work. But I'm under the impression that the reset, it not only sets the program counter to the interrupt vector, but it also sets the stack pointer to another. Let me show you. I'm not sure how it is called, but there is. How can I do this easily? Let me start GDB again. This one, target node, this, and then print, I think it's called vectors? No, vector. What is it called? Do I by any chance export the symbol table? Doesn't look like it. The mapping. Oh, I have to look here. Nope. Maybe look here. Let's see. So the exceptions are in the table. Hey, this one. Oh wait. Does this work? No. Unknown type. Sure, can I cast it to... No. I don't know. So it has interlets. This is what I was looking for. So this is the linker script that's automatically used by the Cortex MRT crate, and this uses. Oh well, this describes how the memory is laid out, and this makes this configures the reset vector. And this should contain the place where, this should contain the placement of the interrupt vector tabel, and that's described here. So it's built up out of a couple of things. So other implementations, for instance, the C implementation that I'm used to, uses one big table with this stuff, but here they split it up, and they start with the stack, the address of the stack, and that is that's the first slot. Then they have the reset vector, all the exceptions, and then the interrupts. Yeah. So as you can see, this the stack location is a slot in the table, and that's used, I think, by hardware to preload the stack register during a reset. So that will prevent us to keep on using the same location or the same stack after the reset has occurred. And typically this is totally fine and a normal thing, but for our goal it is unfortunate, because we want to try to stack the interrupt exception on top of all the other stuff, all the other exceptions, but it doesn't look like that's easy to do, but maybe we can use some trickery. But for now, let's try to just trigger the reset and then worry about how the stack is laid out. So we want to replace the breakpoint with something that will cause the reset, and triggering this is quite easy. There's just a think it's setting a flag or something like that. So perhaps there already is a function for this. I'm not sure, but I think if we look through the register, I think it's also somewhere here. So in the SCB, I think we will find it. So let's do that. Oh, excuse me. Let's see. So here we go, and system control register. Nope. Sys reset request. I think this is it. Asserts a signal to the outer system that requests a reset. Yep. So let's see. To write to this register, you must write a vector key. Okay. Sure. So, and all the other registers, what are they? Can we just leave them untouched? Write only. Reserved for debug use. You must write a 0. Okay, so that's easy. And this is the pre-group, and I think previous video we determined that that had the default value of zeros. So I think we only need to write the key and the reset bit, and that's bit 2. Okay, so let's try to do that. And what's this register called? Okay. So we take the block as before. Then we use the AE. Okay. And then we write something to it. And what's this? This will be trigger software reset. Reset. And what do we have to write? We have to write the key. So let's copy that. And this is placed at 16, and then we have to set the endian and this read only, so it doesn't really matter what we write here, so let's just leave it 0. The priority group, keep it at 0, and this stuff also 0. So we only want to set the bit 2. So additionally, so let's first add for write like this. So now the top half will be the key, and now we want to add in the bit 2, so that will be a 4. Okay. So when we run this, the chips should reset at the end of the chain, and then the whole thing starts again. So this will continuously loop and trigger the exceptions and print them. So let's see if that happens. We'll quit this because we no longer need this. Let's stop this as well and use the regular run. Oh, it's not happy with. I see. So the compiler is not aware that it will not return to this location. So in order to meet the return type of the never return, we have to place an endless loop here. that's fine. And what do we... Oh, I still have the breakpoint? No, what's going on? This is not what I was expecting. So that's interesting. So we get into the enemy, but CPU halted unexpectedly. Hard fault. I'm not sure what to make of this stack trace, but let's look at the code. What did we do? We enter the enemy, then we try to write into the application interrupt and reset control register. Reset control, so this, yeah, I copied that, so that name should be correct. We perform the write, and then it seems like this failed to do something. So maybe this failed to trigger the interrupt, and we still hit this breakpoint, and then we just get this frame. Oh. I think this is a scrolling issue or not. What's going on with that? Yeah, okay, so that was a scroll back glitch. So what happens if we... Maybe it takes some cycles to trigger the interrupt, and before we hit it, we already hit the breakpoint. So maybe just wait in the loop and see if that gives it some more time to let the interrupt trigger instead of halting the CPU. Okay, so this does prevent the breakpoint, but it's not working. It's not resetting the chip, so I think I did something wrong. So the key interesting. Reads, oh okay, so it reads as this, but write should be something else. Should be something else? Okay, so I'm using the wrong key. Okay, but this is, I assume there's only three hexadecimal digits, but we need 4, so I'm assuming there's an implicit 0 at the front. So the implicit 0 and then the key. So let's try this. Yeah, okay. So that was the problem, the key was wrong. And yeah, so they have a different value. So the read, you read this field as FA05, but when you want to write to it, you have to use 05FA. Okay, that means that you cannot do a read modify write accidentally or whatever. But that fixes it. So now we successfully triggered the reset, and the system starts in main multiple times. I think that's also glitching. No, main. What's going on? Main. okay. I think we're losing data. And yeah, so these prints, they are they're using RTT under the hood, and that's a communication protocol used by the debugger to transfer data from the microcontroller to the host, to the system, and that's using a ring buffer. And I think what's happening is we write the stuff in the ring buffer, and it's not picked up quickly enough. So when we reset and we get to the main again, we reinitialize the ring buffer, and that will zero out or reset the pointers into the ring buffer, and that will clear the data that was still there. So in order to prevent that, we should add a delay, maybe, or maybe it's not really a problem. Not sure if there's a flush. If we do a flush here at the end to make sure the ring buffer is empty before we reset the whole thing, it would be nice. So maybe this has a flush, right? Drop. No. Maybe look at the online documentation. So this crate is called entity target. Okay. Docs.rs. I think I'm using the latest version. No, it should not change much. So we have a print. Maybe it's not available. Should be possible that it is aware of the ring buffer. No block skip mode. Blocking mode. How do you configure this? Channel mode. Guess there is a init? No. Default? No. Yeah, this is how you configure it, but no flush. Maybe that's a nice contribution to make. Don't know how useful it is, but oh well. For now, let's not worry too much about it. Maybe we can add some stupid delay somewhere here to see if that fixes it. So let's do for for some time. I don't know, 10,000. The frequency of this thing was something like this. And let's do a knob. That was in core arch. Okay, whatever. Nope. Let's see if that fixes it. Something went wrong. Okay. Try again. Maybe reset the thing. Reconnect. Or was I still... Oh my god, okay. Was I still using the... Was I still using GDB maybe? Not sure. Ah, now it's flashing. Now it... Okay, maybe waiting that long was a bit too much. Now it seems that it's just halted, but it should be busy waiting in this loop. So maybe reduce the number of cycles a bit. Okay, that's still a lot. Another factor of maybe 100. Yeah, okay. So this is. Can I show it? This is continuously continuously resetting the chip, and no longer are we losing the data. We only see main once, and then the cycle repeats itself. So this works. Busy loop to flush RTT. Okay. Let's see how this looks when using the GDB stack trace, because that's a little bit more that shows a bit more information than the one used by ProPares. So we we program the system, so that's no longer necessary, and we can start this. We start GDB and we connect target. We have to start the GDB, the GDB server for this to work. Okay, so now it's connected. Now we can we set a breakpoint in the reset vector? Or maybe set the breakpoint in the NME. NME handler. What's it called? Oh, non-maskable int. This one? Yep. Okay, so now we can continue. Hopefully. Not really working. Is this maybe this is hanging because we're not, the ring buffer is full. In the init. So that's unfortunate. Does this also have maybe some mode to no, it does not. Was hoping that it has some mode that it also continuously to read out the ring buffer so it doesn't fill up, but that doesn't seem to be an option for that. Oh well. So we reset, done, backtrace. Write char. That's unfortunate, because I was hoping to just print the stack frame after a reset to see if it was still there, because to check if the stack register gets overwritten with the value that is placed in the interrupt vector table. Okay. This is, yeah, a bit stupid. So this still works, but maybe we have to change the init in such a way that default mode there's no block skip. So and the size is 1024, but that should be enough to fit one iteration. I would assume, but maybe use another config such that when nobody is listening for the data streams or for the prints, the chip doesn't wait for it when the buffer fills, when the ring buffer is full. So let's see if we can change this to another form of init. So that has multiple with only works in default. Okay. Print debug. No, and print. What's this? Okay. Let's just copy this example because channels. How does this? It's just the init, right? So not sure what the channels channels is used for. What is this type? This is down channel? No. Channel mode. So we want channel mode to be this, and this is not known, so RTT target. And instead of no skip, we want to skip it. Okay. What's that called? Channel. Oh wait, it's no block. As in not blocking, not no block skipped. Okay. So it should already skip data, so it should never wait. What? Okay, so what's the problem then? So this should already do what I want. Right? Default. Yeah. Okay, so this should not be necessary. So what's the problem then? So let's try again. So I start the GDP server with ProPares. That is running. Let's quit this just to be sure. Okay, and run it again, and then connect. That works, and let's then perform. Let's just place a breakpoint at main. Oh, no, breakpoint at main. So there's a breakpoint now, and now we can do a reset. It's not really doing much. Reset halt. Continue. Now we're at main. Okay. Now we can continue. And we're at main again. Okay. So this continuously resets. And probably while we saw it waiting in the send byte, it's because most of the time it's sending bytes then? I don't know. Okay, but this, at least this makes sense. So now we can place a breakpoint in the non-maskable interrupt. Maybe. Continue. That does not work. Okay. What is this code? well, yeah, what I wanted to do is I wanted to place a breakpoint somewhere here and then see if I could step into the reset. If that makes any sense. Maybe that doesn't work. Maybe I have to place a breakpoint in the reset. So let's see if how that's called. Maybe first try reset. Okay. So if I now do a continue, still at main, continue, still. Okay, now I'm in the reset. Okay. So now I can do info reg. I see. Okay, and now. Okay. Now all the registers are 0 except for the program counter that has been placed, that has been pointing to the reset handler. So that's working as expected. And the stack, or at least one of the stack pointers, or the M machine stack pointer, that's the protected, if I recall correctly, but the machine stack pointer is also pointing to a valid location in memory, and this is, I think, the location we saw earlier in somewhere here. So stack start, I don't know where that is coming from. Original RAM plus length. Okay, so that's probably at the end of the stack. And can we verify that? We configured our memory to be 160K. So calculator to programmer mode. Then we can do times. Yeah, okay. So that makes sense. So the hardware is resetting the stack pointer, or overriding the stack pointer with the value that has been placed into the vector table. So when we perform the reset, our stack is, or at least our stack pointer, that's lost. The stack itself should still contain all the frames and all the data. But one of the first things the chip will do is wipe that. So for now, this is, I think, the end. I don't know. So we can claim that we performed the reset, and we do cause the reset handler. That's easy. The chip starts with the reset handler, so that was something we already did. So, but now we also trigger it, and yeah, the only thing we don't see is this stack frame. Yeah. But now, yeah, okay, so now we can, let's see. So now I want to see the backtrace to see that we have all the exceptions on top of each other. But for some reason we could not set a breakpoint in the enemy. Kind of strange. But maybe try the hard fault handler, or maybe these are the trampolines and it's not, we're not setting the breakpoint in the right place. Because when we disassembled this, doesn't really look, or maybe this is a jump, move T. I don't know what this is doing. Doesn't really look complete. Maybe we can try to see what's going on here. So this is doing a bit more, but still not a lot. Mem set. Am I using the right L file? Maybe there's a desync between. No. Let's place the breakpoint in the hard fault handler and see if we get there. So if you continue. Oh, where do we end here? Reset somewhere. Okay. Continue. Main. Continue. Main. No. Reset. Maybe it optimizes everything? No. It's weird. Why does it hit the 4.5e? That's never specified as a breakpoint. What? Kind of weird. Let's loading field. Okay. What's going on with this? Let's quit this. Yes. First check if I see. I'm not using the right. I'm using release here, but I'm probably flashing debug. Okay, yeah, that would explain it. So if I do run release, release, now it doesn't even show what. What's going on? I did not change the print stuff, right? So no, init print. This is the normal one. Yeah, okay. Let's reset the chip just to be sure. Let's reset this thing. Cargo run release. So it's flashing it and it's running it, but doesn't show anything. When we run it without release, it does show stuff. So not sure what's going on there. But for now, let's go back and use the GDP server, and here we use the debug. Okay. Does this work? Warning, couldn't confirm. What? Target node. Oh. Okay. At least we see something. Let's place a breakpoint at the non-maskable interrupt. So let's place a breakpoint here, and we continue. And we hit it. Okay, so this is good. Now we can, run the backtrace. All right. And what do we see? We start at main, sysdig, pentsv, svcall, the usage fault, bus fault, memory management, hard fault, and non-maskable trampoline. Okay. So if we now do info, wait a minute, let's see what, oh. What? Okay. So we do a step instruction. Now we entered the function, the exception handler. Now we can disassemble that again. Okay, and now we should see where the reset should occur. And I think here. So here is the key. So this is, oh, and there's more. Okay. Yeah, so this is the knob. But alright, so I think this is setting up the key in R1 and storing it. Storing it somewhere, okay. Right volatile, okay, so that's not even inlined, but this should cause the reset. So if we run until this, then the setting the reset bit should have happened, and that should trigger the reset. So let's see if we can set the breakpoint at that location. No, we have to use star, I think. Yeah, okay. And then we continue. Do we? Do we hit that? No, okay, so we already reset and we looped around. Yeah. So I actually have to place it just before then, but okay. So this one. Star. Sure, and then continue. Now I should, yeah. I think this is the write to that register. Then let's place a breakpoint at, or maybe step to this. So SE. This should be one instruction. Oh, it's not. I'm not sure what this is doing. Precondition check. Okay. Yeah, just let's continue until... Oh. This triggered it, so... 40, store. Yeah. So this would probably been the write that issued the reset. And if we backtrace now... Oh, we're still... So... Did the reset occur? Info... Not yet. So maybe if we do a single... It's not really happy. Something... What? Sig int interrupted? Oh, those are probably the break... No, I did not set any breakpoints in this function. Not sure. So looks like we're still running. Still running. Still running. Oh my god, a lot of code is being executed. So I'm looking for the reset, and I think this is it. Yep, reset. Okay, so what is this? Pre-init. Okay, so this was one of the last instructions that got run to A52. So that's a store with the register. So probably stuff got loaded into R1 and R2, and then the store happened. So let's use a breakpoint and set it. Set it as a breakpoint, and we can continue to run. And is this the only breakpoint we have? No, still some other breakpoints, but I'm not sure what's going on. Oh, it's the volatile write. Oh, it's a generic volatile write, so it's getting hit all the time. Okay, that sucks. But yeah, what am I even trying to do here? I think we're really done, actually. So we were able to trigger everything, yeah, except for the debug monitor, but yeah, maybe I'll come back for that one another time, but for now I think this is the end. Yeah, let's have a final show of what we achieved. So let's remove all the breakpoints, or most of the breakpoints. So I think only keep breakpoint 2. Oh, that was the one that's not getting hit. So yeah, this is where we ended up, and yeah, it's complete, or at least, yeah, the non-maskable interrupt is the last one we see, but after that the reset happens and the stack gets nuked, or the stack pointer gets overwritten by the reset. So at that point we lose our stack, and thus also our stack frames. But I think this pretty much achieves the goal that I set out to achieve. So I'm pretty happy with this, actually. So I think I will leave it at this. Maybe one day I'll come back and try to include the debug handler. But for now, I think this is the end. So thanks, and bye.